How can we evaluate the limit as x approaches infinity for this expression, x squared over e raised to the x? Well, we could try direct substitution. So if we replace x with infinity, infinity squared is basically infinity, and e raised to the infinity is infinity. Now, this is an indeterminate form. What is infinity divided by infinity? Is it 1? Is it 0? Is it infinity? We don't know. So when you get into a situation like this, you need to use L'Hopital's rule. And the basic idea of L'Hopital's rule is this. The limit as x approaches some number c of f of x over g of x is equal to the limit as x approaches c of f prime of x divided by g prime of x. So basically what we can do is turn f into f prime and g into g prime. We could do so by taking the derivative of the top and the bottom separately. And then maybe we can simplify it into a form that we can get the answer. So the derivative of x squared is 2x, and the derivative of e to the x will remain the same. Now, if we use direct substitution, we still won't get the right answer. It will still be an indeterminate form. So we need to do it again. The derivative of 2x is 2, and e to the x will stay the same. Now at this point, we can use direct substitution. So e to the infinity is infinity, and whenever you have a fixed number divided by an infinite number, you're going to get 0. Anytime you have a bottom-heavy expression where the denominator is very high compared to the numerator, this will give you 0. 1 divided by a large number will give you a very small number, and this is the answer. Let's try another example. Go ahead and evaluate this particular limit. The limit as x approaches infinity of the function ln x divided by x. So if we use direct substitution, this is going to be ln infinity, which is infinity, divided by infinity. So we have another indeterminate form. So let's use L'Hopital's rule. So let's differentiate the numerator and the denominator separately with respect to x. The derivative of ln x is 1 over x, and the derivative of x is 1. So 1 over x divided by 1 is just 1 over x. At this point, we can use direct substitution. So this becomes 1 divided by infinity, which is equal to 0. So anytime you have a fixed number divided by infinity, it will always give you 0. Now let's move on to our next example. Let's evaluate the limit as x approaches 0 for sine 7x divided by sine 4x. Go ahead and try it. So let's jump into L'Hopital's rule, because if we plug in 0 right now, sine of 7 times 0, which is 0, sine of 0 is 0. So this is going to be 0 divided by 0, and we don't know what that is. It could be 8, it could be 1, it could be 0, it can be infinity. So let's use L'Hopital's rule. So the derivative of sine 7x is cosine 7x, and then according to the chain rule, we need to find the derivative of the inside function, which is 7. And the derivative of sine 4x is cosine 4x times 4. So now we can use direct substitution. So if we replace x with 0, 7 times 0 is 0. So we're going to have cosine 0 times 7, and on the bottom, 4 times 0 is 0. So we could cancel cosine 0 because they both equal 1. And therefore, the final answer is 7 over 4. So that's it. So that's how you can use L'Hopital's rule to evaluate limits. Here's another example. Let's try the limit as x approaches 0, sine 8x divided by 3x. So if we use direct substitution, this is going to be 0 divided by 0. So let's not do that. So let's find the derivative of the top and the bottom separately. The derivative of sine 8x is going to be cosine 8x times 8. And for 3x, it's just going to be 3. So now we can use direct substitution. So this is cosine 8 times 0 times 8 over 3. Now cosine 0 is 1, and so we have 1 times 8 over 3, which means the final answer is 8 divided by 3. Now what about this problem? What is the limit as x approaches infinity of x times ln x? So if we use direct substitution, we can replace x with infinity and we'll have ln infinity as well. The natural log of infinity is infinity. And if you multiply a large number by another large number, you're going to get an even large number. So infinity times infinity is infinity. Therefore, this is the answer. Now what about this example? What is the limit as x approaches infinity of x raised to the 1 over x? Now if we replace x with infinity, it's going to be infinity to the 1 over infinity. 1 divided by infinity is 0. And infinity to the 0 power is indeterminate. So there's nothing we can do right now except using L'Hopital's rule. Now we don't have a fraction, so we need to use a different process here. We're going to set the original expression equal to y. So y is equal to the limit as x approaches infinity, x raised to the 1 over x. Now we need to take the natural log of both sides. The reason why we want to do that is because we can take this and move it to the front now that we have a natural log in front of it. It's one of those properties of logs that you need to know. So we have 1 over x times ln x, which we can write that as a fraction. So we could say that's ln x over x. So now we can employ L'Hopital's rule on the right side. So the derivative of ln x is 1 over x, and the derivative of x is 1. And so we have the natural log of y is equal to the limit as x approaches infinity, 1 over x. Using direct substitution on the right, we can see that the natural log of y is equal to 1 over infinity, and 1 over infinity is 0. So ln y is 0. Now the base of the natural log is e, so e raised to the 0 power is equal to y. And anything raised to the 0 power is 1, so y is 1. Now recall that y was equal to the limit as x approaches infinity for the original problem, x raised to the 1 over x. So we know that y is 1, therefore the limit as x approaches infinity for x raised to the 1 over x is 1. Now let's check the work. Let's see if we indeed have the right answer. So let's make a table. And let's plug in some values. So let's pick a large number. Let's start with 10. So 10 raised to the 1 over 10. As a decimal, that's about 1.2589. So it's relatively close to 1. Now let's choose a larger value for x. Let's try 100. 100 raised to the 1 over 100 is 1.0471. So it's getting closer to 1. So let's try 1,000. 1,000 raised to 1 divided by 1,000, that's 1.0069. So as x gets larger and larger as it approaches infinity, we can clearly see that y is approaching 1, where y is basically x raised to the 1 over x as x approaches infinity. Let's try one more example. What is the limit as x approaches 0 of 1 minus 2x raised to the 1 over x. Go ahead and try that. So first, we're going to set that equal to y. And then we're going to take the natural log of both sides. So ln y is going to be the limit as x approaches 0, ln 1 minus 2x raised to the 1 over x. Basically, I reversed the equation. I want y to be on the left side. So now that I have the natural log, I can move the 1 over x to the front. And so I can write this as a fraction. So I have ln 1 minus 2x, and instead of multiplying by 1 over x, which is the same as ln 1 minus 2x divided by x. Now let's use L'Hopital's rule. Now what is the derivative of ln 1 minus 2x? To differentiate natural log of u, it's going to be u prime divided by u. So it's the derivative of the stuff inside, which is going to be negative 2 divided by whatever was on the inside, which is 1 minus 2x. And the derivative of x is 1. So what we now have is the natural log of y is equal to the limit as x approaches 0, negative 2 divided by 1 minus 2x. So now we can use direct substitution. Let's replace x with 0, so we no longer need to write the limit expression. 2 times 0 is 0, and so what we have is 1 minus 0, which is 1. So therefore, ln y is equal to negative 2 over 1, or negative 2. And this is base e, so e raised to the negative 2 is equal to y. And so once you have the value of y, you have the final answer, which is e to the negative 2. So we can write the original problem. So we can say that the limit as x approaches 0 of 1 minus 2x raised to the 1 over x, which this whole thing equals y, and y equals e to negative 2. So the limit is equal to e raised to negative 2, which, if you want to, you can write it as 1 over e squared. Both answers are acceptable. And that's it. So now you know how to use L'Hopital's rule to evaluate limits of the indeterminate type.